Good afternoon and welcome to the Security Seminar from Purdue University, CERIAS Security Seminar. Our speaker today is Mr. Joe Leonard. He is the Director of Technology from Global Velocity. Their company produces an interesting network security appliance that he's going to be speaking about the inner workings of in this talk titled Methods and Techniques for Protecting Data on the Wire in Real Time. Joe?
Thank you, Randy. So first of all, I would like to thank SPAF and Joel Perkins for sponsoring this presentation today, for asking us to come in, and thanks to Randy for hosting us, being a very good host for us today. So without further ado, we'll get into this. So I'm here today to talk about, as Randy said, I'm from a company based out of St. Louis called Global Velocity, and I'm here to talk today about something very near and dear and important to us and what we are trying to deliver to the marketplace. That is methods and techniques for protecting data on the wire in real time. Please, as we go through this, feel free to interrupt me with questions. I understand that everything will be recorded, so I won't have to repeat questions if you make sure that you talk in your microphones. But I don't mind this being interactive. In fact, I would prefer it to be interactive as opposed to having to come back to things at the end of the presentation. So we're going to go through a few things today. First of all, we're going to define a problem, what we see as a very serious problem today, and in fact, the problem that drove the initial development of some of our underlying technology. So we'll talk about that problem, define it. We're then going to talk about deep packet inspection, which in our case is the foundation or the groundwork for attempting to at least solve that problem. Then we're going to talk about sophisticated content search mechanisms and inspection. This really gets to the core of what we wanted to get across to today. Because content, really, at the end of the day, we can talk about firewalls, we can talk about perimeter protection and defenses all day long. But at the end of the day, what we're really trying to do is protect intellectual content or digital data that lives behind those perimeters. And that's what we're trying to address with our approach. And then lastly, we'll just spend a brief moment on turning that around and using that same technology to not only protect content as it's moving about the network, but also how to use that same types of technology to look for data of interest that may reside on various file shares or out in the wild on the internet, things like that. So problem definition. A couple slides here, but so first thing we need to get across, and a lot of this is not new to anybody that's in the networking industry today, but as we all know, information is the new currency. We've moved to a digital environment, and what that data is really very widely varied and dependent upon what type of organization you're in, company you're in, industry you're in, etc. And we'll look at that very briefly in a subsequent slide. Another thing that we all know, we're no longer dealing just with college kids who want to get their name in the paper. The bad guys are growing in their sophistication. They're relentless. We have an entire cyber criminal environment out there now that's a very big business, and it's growing both in size, complexity, and sophistication. We also have nation state espionage that we have to worry about today. So there's a lot of elements to the bad guys out there that we need to be aware of and watch out for and protect our digital assets from. We're going to talk briefly about network speeds, application complexity, and how that drives the need for newer techniques around looking inside packets as they're flowing across the network. I just mentioned the fact that traditional perimeter defenses are not enough. Just building a wall around the castle or a moat around the castle, so to speak, is still necessary, and we need to stay on top of those technologies and constantly evolve. But no matter how good we get there, we can always count on a few bad guys getting through. Add to that the fact that we have insiders, whether they're intentional or whether they're just mistakes. Mistakes do happen, so being able to protect ourselves against those types of actions are good and necessary. So, information-based economy that we live in today, what are the bad guys after? It really depends. I mean, it's intellectual property. Our own company, for example, we have trade secrets and things around the development of our applications and platform that we can share. We enjoy sharing a certain amount of that with our customers, with our industry partners, etc. But there are some elements that we want to keep to ourselves, because if allowed to get out into the public realm, then somebody else could replicate exactly what we've done, and that would take an opportunity away from us. Compliance. We're all consumers. I care about what my credit card company or my retailers that I shop with, I care about what they do with my information, because if they don't handle that information correctly, if they don't protect that information from loss, then the next thing you know, somebody's got my credit card information and I'm paying for somebody else's vacation in Cancun, right? So business operations, government and defense, obviously you can think about a lot of examples in the defense industry and in our government industries where information is of utmost, information secrecy and protection is of utmost importance. And you could go on all day long with coming up with examples depending upon your perspective and where you come from. Bandwidth. I'm not going to spend a lot of time on this. Everybody in this room knows this. Network speeds are going through the roof. I can remember, showing my age here, when 300 baud was considered new. A 300 baud connection was really something. So I've watched the evolution of our networking capabilities go from up into the megabits to gigabits, and now we're talking 10 gigabits. We've got 40 and 100 gigabit networks now running across carrier backbones. That's finding its way out into the campus arena. And in the standards bodies, we're talking about terabit Ethernet. So some very, very fast speeds. And we'll talk about why that's important in a moment. At the same time that we're looking at these vast speed increases, we're also seeing an exponential growth in instructions per packet in terms of processing on the network. So if you back up to the days when all we did was route, when we started interconnecting networks and we're using switching and routing, we're talking about 50 instructions per packet or so. It's a very, in today's terms, that's nothing, right? In those days' terms, it was considered quite a feat to be able to do that kind of take that kind of computational action or activity on packets flowing across a high-speed network. Today, as you move up through VPNs, you move into intrusion detection, advanced application firewalls, and finally into content filtering, where we're actually looking at the content in the payloads and doing something with that content, manipulating it, looking for things of interest. Now we're up in the 45,000 instructions per packet. It's a huge increase. So that increase in processing power requirements, when coupled with our speed changes, brings us to a point where we actually see two paradigms now knocking up against one another. So Moore's law, of course, we all know that, processor capacity increases, roughly doubles every 18 months or so. Well, Gilder's law on the networking side has now surpassed Moore's law. The problem that creates is that traditional approaches to processing network traffic just don't cut it anymore. Traditional approaches being one of two, either processors, soft-core processors, very, very flexible. You can do anything you want as long as it's not too fast, right? Or on the other hand, if you need speed, then you figure out what you want to do. You stamp it out into an ASIC. ASICs being hardware are very, very fast, but they're very inflexible. The problem with that is that as requirements change and new applications come out, new threats, new capability requirements, that ASIC now puts you in a position where you're looking at forklift upgrades, and people with the pocketbooks don't like forklift upgrades. So we think that there's a better approach, and we'll talk about that approach in a moment. But first of all, let's talk a little bit about deep packet inspection in terms of what that means for application control and in terms of getting to not just controlling applications, but then giving you the visibility and the capability to go into the payload and pull out exactly the content you're looking for and examine that content for various purposes. So as we all know, when deep packet inspection as a technology and as a term has been around for quite a while, but it has evolved, as many things have in the networking industry as time has passed. The time was when if you did anything beyond routing, you started looking at ports and protocols. That was considered deep packet deep packet inspection. And in fact, today, if you talk to a router manufacturer, he'll still tell you that he has deep packet inspection capabilities if he's doing nothing more than looking at ports and protocols. Then we get into the late 90s, mid to late 90s, and we start looking at stateful inspection. Okay, that was deep packet inspection, being able to look at port changes, dynamic port allocations based upon application requirements. Then we fast forward into the internet age when the web really takes off and we start looking at Web 2.0 and everything's running across port 80. Now we're looking port and protocol is no longer good enough, because you can't just shut port 80 because I don't want a particular application running. There's so many applications running on port 80, or pick your port, other ports as well, that are required now for just for normal operations, for business, etc. But the ability to look inside, so where we are now with in terms of controlling applications on the network is we're using regular expression type analyses to determine various components of an application. So I can tell today with advanced regular expressions that can be used in a deep packet environment, I can tell the difference between, let's say, a Facebook logon, a Facebook read, a Facebook post, a Facebook attach, a Facebook chat. All of those can have their own unique signatures associated with them. And as a network device, if I have the ability to look at the data stream at very high speeds and identify those flows based upon those signatures, I now have the ability to not only inform somebody what's going on in my network, but I now have the ability to control those applications. So, and that is very, very important. But ultimately, at the end of the day, what I really am after today is the golden egg at the top, that being content. Now, I can't get to content if I don't do all of those other things below it. I can't even, I mean, even if I do dynamic port stuff and things of that nature, stateful firewalling, that still doesn't give me enough visibility to actually peel content out of the data stream and look at it. So that's a very important component of deep packet inspection. So I said in the previous slide, we talked a little bit about software processors, and we talked a little bit about ASICs and their strengths and weaknesses. FPGAs, now on the other hand, FPGAs are nothing new. Field programmable gate arrays, or programmable hardware, if you will, have been around for quite a few years. The interesting thing is that they have really been on a growth curve in terms of their capabilities over the last 10 years, and they're really some very interesting and capable silicon devices these days. At Global Velocity, we were able to leverage some early work out of a university in St. Louis called Washington University. Many of you probably know that university. Where some early researchers looked at these exact problems that we just discussed and realized that we were going to have to come up with a new way to approach deep packet inspection and filtering in the future. And so they spent a lot of time looking at FPGAs, and we've been able to leverage that early research into what you see from us today in our capabilities. The beauty of FPGAs is, again, the fact that I can now run at very high line rates. In our case, we're running at speeds up to 10 gigabits per second. But I still have the flexibility that as the application environment changes, if I need to change an application signature, Facebook, for example, since we're picking on them, they change their application fairly frequently with new capabilities, new, security bug fixes, things like that. That has the effect of effectively changing their application signature on the wire. So now if I'm going to continue to be able to identify that application on the wire, I have to be able to adapt to or change my signatures to meet that challenge. So hence the flexibility, the importance of the flexibility in FPGAs. So again, an FPGA, very quickly, just to recap, gives us the power of hardware in terms of speed. It gives us the ability to update. They're also remotely programmable. So if I put in the right gates, I can get into those devices remotely and actually reprogram them on the fly. I can even reprogram sections of an FPGA so that maybe most of the hardware is still doing its job, but maybe I'm just updating the memory mapped portions of the FPGA to my new signature base, for example. Another great advantage to FPGAs is the parallelization that you can get, and the pipelining that you can use, that you can get, capabilities that you get out of an FPGA. When you combine that with multi-core general purpose processors, the capabilities really get very interesting. So this is just a slide screen of our device, and just to drive home the importance of the ability to be able to not only see, but be able to control applications on the wire at these speeds. Come on in, sure. So controlling applications on the wire is important for a couple of things. Maybe there are applications that are inappropriate for my environment. If you think of a corporate environment, for example, peer-to-peer, applications. And I know there are people who are trying to promote using peer-to-peer applications for some legitimate purposes. But for the most part, corporate America still sees peer-to-peer as nothing more than a band hog, and it's taking away worker productivity. So the ability to see peer-to-peer applications and stop those, and we all know that they use various ports, they jump around, so you have to be able to look at signatures to be able to do that. That's important. To go back to our friends at Facebook again. Well, here's an application that when it first came out, again, it was a time waster, and corporate America said, let's just turn it off. But then marketing comes to the table and says, now wait a minute. We're now communicating with our customer base via Facebook. It's a useful tool for us. So now I have the ability to allow, and you can go on beyond that, and you can get into, well, mom and dad now communicate with their kids over Facebook, so I need to know what's going on. Is the babysitter going to be there tonight, or can I stay and work late in the evening? So access to, and varied levels of access to these applications becomes more and more important. So now with technology like we're looking at here, I have the ability to block some applications completely. I can open other applications up completely. But in between that, there's all this gray area that, depending upon who I am, what my drivers are, what my security posture is, what my corporate policies are, my organizational policies, I can actually fine tune and actually provide some very fine-grained controls on today's application environment in the Web 2.0 and 3.0 or 20.0, wherever we're going, right? So application signatures, just a quick look at signatures. If you're not familiar with regular expressions, this gives you a quick look at how to create regular expressions. I'm not going to spend a lot of time on this because this is something that if you're really interested in and you're not familiar with, you can do some searches on the internet and come up with a lot of great tutorials on writing regular expressions. We use it today. We're using it for application definition and identification, but it's also used looking for viruses. It's used by other organizations. Most of our intrusion prevention, IPS, IDS vendors use regular expressions to identify things that they want their devices to look for as well. So it's becoming more and more a commonplace skill set in our security and security organizations. For us, the key, the most important thing beyond just looking at the applications again, is being able to go down through the stack. A quick look at how this works going through a device, for example, a network-based device, is first I capture my Ethernet frames. I then have to reassemble my TCP flows into a logical, organized approach. I get rid of dirty packets. I get rid of incomplete flows because that only wastes valuable processing time at a higher layer. Get rid of those. I can then do all of my application control, again, in our case, in hardware, in flexible FPGA hardware. I can then I can identify in that flow exactly where the content is. Content being whether it's pure text, straight text, HTML encoded text, or more elaborately encoded text like an attachment, a Word document, or a PDF, or whatever. So being able to identify that, to strip that out, and then send that up to a higher level processor for a quick look for things of interest. Things of interest being either, we'll look at in more detail in a moment, but it could be patterns, it could be keywords, or it could be fingerprints associated with. Yes, ma'am.
I have a question.
Yes.
Perhaps it's a naive question, but what if the payload is encrypted?
Okay, very good question.
Yeah.
If the payload itself is encrypted, there's not a technology today. The only way around that would be if you have the keys to it.
Actually, today there is a lot of techniques using which you can search on encrypted data. Perhaps it's not very efficient, but in any case.
Well, let me ask a clarifying question then. Are you talking about encrypted payload, or are you talking about encrypted path?
I'm talking about the encrypted payload. So
Okay.
suppose you attach a document,
Right.
and this may be encrypted. Because I've seen a lot of attacks, especially for data exfiltration, where really the content is encrypted before even trying to send
Sure,
it out
sure.
of the organization.
Sure.
Because we are also doing a lot of work. So a question I always said when I was looking at packet inspection is, what if this thing is encrypted?
Sure, absolutely. And so I guess the comment I would add to that is encrypted content, and you're right, for certain types of encryption today, there are methods and mechanisms, some of them fairly processor intensive, But there are methods that you can open that up and look at it, that you can crack the encryption and get into it. But that's really going to be a function of the sophistication of the encryption used, right? If it's, 256-bit AES or something, then it's going to be a bit more difficult than, a 128 or an older type of encryption format, right? But a very, very, very good question, and we could spend a whole hour or day on that topic alone. So, okay, so now we're going to go into the actual ability to look into the content payloads and what to do about, how we're going to actually protect that, right? So when we talk about content, there's really, in my mind, there's three types of content that we typically see today. You have content that comes from databases, okay? That's structured data. It comes in rows and columns. It's very structured. When it comes out of, and there's a lot of mechanisms today around being able to protect databases, controlled access and all these kinds of things. But once the content comes out and gets on somebody's desktop and they manipulate it, it becomes something very different. In fact, then it becomes more like our second category, that being unstructured data. Unstructured data is file shares, websites, any type of storage repository that can have a variety or a number of different file formats just stored in it. So you can have Excel spreadsheets, you can have PDF documents, PowerPoints, Words, and the list goes on and on. For example, we've got over 400 document encoder components within our system to identify over 400 different file types. A lot of them are obscure, not used very much anymore, but still, if you're going to be in this business, you have to have a pretty broad base to work from. So unstructured data is the second type. The third type is freeform data. This is somebody sitting at their computer and they're typing something into a blog or into Facebook or into their web-based email, or maybe they're just free-forming an email in their SMTP, their Exchange email account. But they're typing in information and then they're hitting send or taking some action that now sends that data across the wire. So those are the three types of information that we really want to be aware of and address as we start to look for those things. Now, so I've shown you that by controlling the applications and identifying where the payload is and peeling that out, now I have something that I can hand up to a higher level processor. Unfortunately, FPGAs have still not gotten to the point to where they can do this piece. So this is where the multi-core stuff comes in. So you bring in multi-core processors and you have applications that go through a number of processes where you can first, and there's different people do it different ways. In our case, we go through a normalization process where we strip away any encoding. We turn it into just straight UTF-8 format. We compress that, take out all the dead space, punctuation, capitalization, all that kind of stuff, so that all you have is the intellectual content. Okay. And now you've got something to search, and you can search for one of several things. First, I can look for strings or patterns. Strings and patterns. This is probably without a doubt, this is the first approach when data loss protection first started hitting the streets several years ago. This was the first approach that vendors tended to take was, well, let's look for strings or patterns. Let's look for things that look like social security numbers or things that look like credit card numbers. And it's a good approach for some purposes. What we discovered early on, though, is it's very false positive prone. So any type of pattern that you're going to look for, you really have to make sure you've got some good validation algorithms around those patterns. And I would say that even then, it's still not a good stopgap or end game for looking for data. It's a good discovery tool. That's how we feel about it. It's good for plugging a device into a network. You can turn on the device, start seeing what applications are running, develop a quick little 2-minute policy that says, look for, tell me anything that you see that has social security numbers in it. Okay. And then you'll very quickly start to see where content's coming from. You'll see kind of where it's coming from in your organization, because we'll collect all the flow information that says who is sending it, where they're sending it to, and collect the actual content and give you a representation of that. You can very quickly determine, well, is it false positives or is it something of significance that I need to go take a closer look at? Do we need to take a look at our policies? Or do we have employees or users that are not following policy? Do we need to address that? So it's a good discovery tool. The next method that I would briefly touch on is regular expression matching or context matching. So this is whether you're creating dictionaries of terms or phrases, or whether you're doing the more complex regex, just like we did in the application space, you can do kind of the same thing in the content space, and you can try to do some proximity and some context-based stuff, right? You can do that, and it can be somewhat useful, but again, it's going to be very, very false positive prone. Dictionaries by themselves, without using regular expression matching, can be useful, but again, it's good for looking for information in free form. A good example of where dictionaries are very useful would be, for example, if you have a financial organization that does stockbrokering. And in fact, we have a customer who's looking at this as a possibility, a very real possibility. They want to be able to start allowing their broker community to use tools like instant messaging, but they don't want them, providing advice to their clients. So how do we do this? Well, if you've got the ability to see the application and you've got the ability to look inside the content flow for keywords like buy low, sell high, pick your poison, but you get the idea. Now they can actually allow them to use these more advanced, these newer applications, although instant messaging, some would argue, is not a new application. At my age, I still consider it new. But the ability to actually allow your users to use these applications, but look and make sure that they're being compliant in terms of what they're doing on these applications, is a useful tool. So dictionaries have some good, useful purposes. Ultimately, at the end of the day, though, what we believe is the most efficient and best approach is fingerprinting the exact data. And this can be done on structured data as well as unstructured data. Free-form data, you can look at that and look for similar things. So somebody could actually type content from another document that's protected, and you would catch that. But free-form, it's not as typical. But certainly structured data and unstructured data, fingerprinting is a great example of how to do things. And let me just look real quick before I get too far ahead of myself. So content matching versus known content versus regular expression matching. So when we talk about exact content matching, there's typically a pre-processing piece component that's involved. In our case, we have an application called an indexer that you identify the content that you're interested in protecting. Let's say it's a CIFS directory or a website, an internal website, for example. Once the indexer knows about that content source, it then goes and pulls a copy of everything from that source. It goes through the exact same process as I just described in the scanner. It's going to normalize it, turn it into just raw text. It's going to run a number of rolling hash algorithms against it to create a number of fingerprints for that content. Ideally, the larger the document, the more fingerprints you're going to create. And the fingerprints will be structured in such a way that you're going to minimize false positives, but at the same time, reduce the window size of your hashing algorithms to the point to where a typical cut and paste or a copy out of a protected piece of content would still be caught. And that is a challenge, trying to get that fine line between making sure you catch anything that gets cut and pasted versus catching all kinds of stuff that you didn't really intend to catch. So, but that's a piece of the tuning algorithms that go into a deployment. Advantages of this process: they're easier to configure. You don't have to, as opposed to regular expressions, you don't have to write all the rules. You don't have to tell it what to look for. You merely point the indexer at the content that you're trying to protect. It's going to be looking now. It's going to create fingerprints off of that exact content, not a facsimile of or something near to that. So it allows for structured data matching. Where a database comes into play, there are some middleware pieces that you can take into account. You can do weighting assigned to various either tables or columns or amounts of data. You can set priorities based upon number of records, things like that. So, then finally, the last major advantages that I'll mention here is the ability to protect partial copies of content. So if somebody, for example, pulls an Excel spreadsheet with financial data out of a directory that's being protected and just scrapes some of the data out of that spreadsheet, drops it into a Word document, puts some free-form text around that, turns that into a PDF, zips it up, and tries to send it out of the network. When the network device and the scanner sees that content, once the application piece does its piece and strips out the content, sends it up to the content scanner, the content scanner will now go through that same process of creating fingerprints out of that live data. And it's going to then compare those fingerprints to what it's been told to protect. Now,
I have a quick question.
Yes, ma'am.
So is that a hash function that are you using, or is it more a Bloom filter
this is hash functions.
as hash
These
functions?
are hash functions,
Okay.
yes.
But must they have some specific properties, these hash functions that you are using?
Okay. We'll talk a little bit more.
Okay.
If my slides don't cover it, I've got a couple of documents that are publicly available that I can share with you as well. So how are we doing on time? We're looking at 20 minutes, is that right? Okay.
Yes.
Okay. So I've kind of talked to this already, but we're going to spend just a couple of minutes making sure I didn't miss anything in terms of how we do content fingerprinting. We identify the content basically, we normalize it, we fingerprint it, and then the fingerprints are obviously stored on the high-speed network appliance so that it can watch for this content going by. We talked a little bit about this. So this is a little bit of a recap. But basically, we strip everything down to a common UTF format. We then run our hash algorithms against that, and we'll talk about those here. So our hash algorithms are set so that, I'm sorry, I'm getting ahead of myself again. So once the information's been fingerprinted, though, and they're in the hash database for the scanner can now watch for this information flying by. Now, one thing that does occur typically is in a lot of organizations, you'll have information in secure documents that really isn't that sensitive. Header and footer information is a great example of that. An organization will have common header information on a lot of their documents, whether it's important stuff or non-important stuff. So if you've now fingerprinted content that has that type of information in it, what do you do about that? That's going to create false positives. So it's also important to have tools available in your system to be able to very quickly winnow through that kind of stuff and eliminate it from future future hits. So another advantage of this fingerprinting process is, as opposed to trying to look through, as I see content on the wire, some time ago the approach was suggested that, well, if you have an exact match of everything that you're trying to look for, you can just look through that database. But the problem with that is twofold. First of all, it's very cumbersome, requires a lot of storage as well. So another advantage of going through a fingerprinting process is you're effectively reducing your protected content down to a very small representation of the actual content that you're trying to protect. Again, the fingerprints that we create are distributed across the document. When we go through our fingerprinting process, we're hashing through all of this information. If you look at this particular example of a document, for example, you would find fingerprints throughout there. The whole thing would not be a fingerprint, but you would find bits and pieces that are very unique to that document. So unique threats, so there's two thresholds that we look at when we do fingerprinting. There's a unique threshold that is based upon a sizing window. So as you can see in the example here, you don't want to catch you don't want your window to be so small that these two examples would both fire off would fire off a positive, right? A positive hit, because one of them would be probably false. So by increasing your window size just a little bit, you can eliminate those types of issues. So the second threshold that we set are match thresholds. Match thresholds are used to make sure that that in any sequence of tokens or characters in a document, based upon your minimum threshold, for example, a threshold of 100 would guarantee that any run of 100 characters from a protected document would generate a hit, right? If you go smaller than that, then depending upon where the fingerprint resides, where the unique characters that are being used for the fingerprint reside, it may or may not. And in fact, we found in practice that oftentimes, a very high percentage of the time, that we're generating hits on much smaller bits of information than that match threshold. However, the match threshold guarantees that nothing larger than that would get through without being caught. So another impact of this piece also is the amount of memory, because all of these hashes are stored in memory on the high-speed scanner. So obviously, the larger your fingerprints, the more fingerprints you have, the fewer documents you're going to be able to protect. So the ability to fine-tune those things and get the most bang for your buck is obviously very important. Content format, I mentioned this earlier. We use plugins, and I think that's a very common approach, using document encoding plugins that are able to understand and decode the various types of content that are out there. As I said, I think we've got over 400 content types that we can identify and normalize down to UTF format. I'm going to talk just very briefly about databases. I want to make sure we don't go over. Databases require a little bit different approach, because you can't just fingerprint an entire database. Data comes out of databases and is used in a variety of ways. One person may pull out, do a query that returns a certain bit of information. Now it's on their desktop. Somebody else goes in and does a different query for different purposes, and they can get completely different information on their desktop. So typically what we have to do is we go through a few steps when we're working with a database or any kind of structured data. First thing is you analyze it. You sit down and you look at your rows and your records and the relative importance of, for example, the name Joe is, I don't care about that. I can see that go by in a data stream all day long, and I don't care about stopping that. The name Joe Leonard, well, now that's interesting, but there's a lot of Joe Leonards. Now if I see Joe Leonard and I see a social security number from my database, now that's very interesting, and I may want to be able to do something about that. The other thing would be sometimes one approach to sifting data out of a database would be to take rows or columns of information out. So, well, maybe Joe by himself is not so important, but if I see Joe, Frank, Fred, and 50 other names that happen to be in my database go by at the same time, well, now something's going on. So I probably want to know about that and may want to do something about that. So you go through an analysis piece where you take the time to look at the database with your DBA, with your customer, and you just determine what's most important, what combinations of information are most important, etc. We then develop a middleware piece that will query the database and pull copies of that content. You're not necessarily pulling a copy of every record. You're pulling specific columns of information, and you're pulling every so many of rows based upon let's say your risk threshold. What's important to me? Is it one record? Is it 100 records? One record is normal business. I don't want to hamstring normal business, so I have to make some decision points, have to make some calls on what's important and what's not. So my indexing process on the database will pull the appropriate information out, and I then turn that into, in our case, we turn it into an XML format and store it in a directory that our scanner now our indexer that we discussed that's doing the indexing for unstructured data, it now can do a very similar process to this content that came out of a database. Now, as far as then the last piece involved with this is keeping that information fresh and up to date. Well, both our indexer as well as the middleware piece that's going to extract and create the XML content, both need to be set on a schedule. Again, it's going to be based upon business requirements, actual requirements. How often does the database change? Does it change every 5 minutes, every 5 days, every 5 weeks, right? And based upon those decision points, we can get very granular on how we create our protection scheme for this database. I've got a couple more slides here that I'm going to skip past that I've really talked for the most part through on the database. If anybody wants these slides, you're more than happy to get a copy of them, and the information will be, if you want to follow up, you're more than happy to. But I want to get to this last piece real quick. So searching for and identifying critical data at rest. So one thing that we hear a lot when we're in front of customers, whether it's academia, whether it's industry, federal, etc., is, boy, I want to I want to get a handle on this stuff. I know I need to protect my data, but gee, I don't even know where it all is. So if we go back to our discovery process, right? I talked about things like pattern matching, have some useful purpose in discovery, finding out what's going on in my network. So if I plug a device, an intelligent device into my network that can see what's going on first, it can tell me what's happening with my applications, it can tell me who's running what applications, where they're running these applications to, and then I can start to look at some pattern matching. Maybe I want to look for some keywords. Maybe I'll create a dictionary or download a dictionary of terms that I want to look for that are of interest, depending upon my industry. That could be very different from one to another. But I know the basic stuff that I want to look for and see what's going on. Now that's going to give me information that I can now use to create policy. It's also going to tell me, where's my information coming from? What information do I need to look at? So that's going to give me some idea of the kind of information that I'm looking for that's of interest to me. And now I can use our fingerprinting process to go fingerprint exact copies of information. And as we all know, in today's collaborative environment, I may start a Word document. Well, I'm working on a team. I want 3 other people to comment on it. So I email it out, or I put it out on a file share or something for you to look at. Well, then you make a copy of it, put it on your desktop. Well, this goes on and on and on until you've got something that's spread out across the organization. So a lot of organizations are really concerned with, well, I know I need to protect this data, this content, but I don't know where all it exists. I don't know where there's other copies of it. So help me with that. So it turns out that because we've developed all this to do on the network in high speed in real time, that I can also use the same process and technology to turn it around and look for content of interest. That can be content either within my organization, or if we look at, I know we're all getting tired of hearing about WikiLeaks, but I'll use it as an example anyway because it's a great example. Okay, so the government knows that this stuff's out there. It's secret. We know exactly what it is, but where all does it exist now? So if I have some idea where to look, I can actually employ web crawling technology and things like this along with this technology. And I can now pull down content, and I can either search that content as I'm pulling it across the network from the wild and say, aha, I see a storage site right here. I need to go see if I can do something about this. Or I can even pull it down and just suck it down into a repository and then search that repository at will at a later point in time. So. So that is, I believe, everything I've got for today. I think we're real close to, I think we've got about 5 minutes left or so. Does anybody have any questions or comments? Or you're asking great questions. Keep on asking.
No, I have, but perhaps the audience has questions. I don't want to monopolize the
Sure.
speaker. Okay, so, yeah.
I was wondering about objects that may be hidden through steganography, like hidden inside of another, maybe a PDF hidden inside of an image file or something like
question.
that.
Great question. The approach that we do when we go through our normalization, as you may be aware, most of our files today are actually combinations of a lot of files. I mean, the average user doesn't realize that, doesn't know that. Now I've got a PowerPoint. PowerPoint's a great example, or PDF is a great example. But in fact, you tear that thing apart at the file structure at the bit level, and you find that there's a number of files nested within that document. So our normalizer, I'm drawing a blank. Our process for turning that into UTF-8, for example, when we go through that process, it actually goes down into that level and breaks it all out. In fact, if I could show you an example in one of our live systems, you can drill in, and in the content manager where you set up the stuff that you're looking for, you can actually see all the sub-document types that are within any given file. So if somebody had hidden something, that would become apparent there as well. So, okay. Yes, sir.
So, I actually have 2 questions if you have time. The first one is,
You turn your mic.
You need to turn on your mic, sir. Okay.
Currently, we see that there is, the packets are being tunneled when it comes to, IPv6 to IPv4. Do you have, I'm sure you should have some, at least the basic technology to inspect that, but do you have, better technology to inspect the packet that's in that?
So, yes and no. So, excuse me. So the way our processor is working today, within the FPGA code itself, there's a number of different modules. The very first module that As the data path comes through the FPGA, the first module that it hits is a protocol decoder. In most cases, it's a TCP, because most of the applications that we're talking about here are TCP based applications. So you're looking at a TCP protocol component. For other types of data, then you would merely replace that TCP module with the appropriate one, whether it's UDP in V4 or as you get into V6, then it's got its own set of applications and protocol types, right? So.
And the second one is basically, so when you develop your hardware and your software, do you also look at, other network analysis software like Argus, which is basically being developed by Quotient? I mean, that is one of them that actually has the ability to detect and, figure out encrypted packets. Not to a very good extent, but it does some kind of statistical analysis and it figures it out. That's why I was wondering if you have anything of that line.
We have not yet. To be honest with you, our first piece to tackle in the encryption space is encrypted path. And we have a method for that, and the only method around that is to do a proxy element. Our proxy approach to encrypted path, just as a related side note, is a little bit different from the normal proxy firewall approach for encrypted traffic, because since it's a component of our device, we merely need to proxy the keys, and now since the data path is still coming through the same device, we can now rejoin that traffic, that unencrypted traffic, to go through the rest of the process as though it were unencrypted in the first place. But the encrypted components themselves, encrypted files, we've not even begun to, quite frankly, look at that. To be honest with you, most companies aren't even asking for that yet. Right.
That's true, because actually, in a way, I talked to several organizations. They told me, actually, if you see encrypted traffic, that may be already a suspicious something.
Right.
But I've seen a lot of attacks where indeed those.
Absolutely. So our approach so far for encrypted content and for encrypted path to a certain extent is if we can identify it, if you have, for example, a corporate policy says, here's the accepted encryption algorithms and here's your keys and all this kind of stuff. So you've got a policy around encryption. We can't enforce that. So if we see rogue encryption, something that I don't recognize, I just don't allow that. And that's, in most organizations today, that's the expected approach.
Yeah, and actually my idea was exactly to say that only certain parties are authorized to encrypt,
Yes.
and before they will inspect the content. So they inspect, then they encrypt, and then this traffic can go through.
Absolutely.
That's one possibility,
Absolutely.
because,
Because I think in most cases, organizations that are using encryption, especially at the file level, they've got a fairly strong policy, and if people are going through the process of encrypting, then they're pretty comfortable that it's going where it's supposed to go. It's what it's supposed to be. And if it is intercepted anywhere along the way, it's not going to do anybody any good anyway.
you can exactly, check who has assigned something,
Yes.
and then you can detect if it's not an authorized person.
Absolutely.
Yeah.
I mean, but if you actually look at it, the policy is itself a workaround. I mean, it is not enabling you to, improve the technology. It's just that it's helping you go around it.
I would accept that. And it's just, so that's another one of those whiteboard futures things for us. It's as the technology improves, as the ability to do. On the other hand, as a user, I frankly have concern over the ability to, if anybody can crack open encrypted packages, that kind of defeats the whole purpose in the first place, right?
No, but there are a lot of advances in cryptography
Yes, right.
today that you may do something.
Right. Absolutely. If somebody's using 10-year-old encryption technology, then they deserve to be hacked. So anyhow. Any other questions? Okay. I think we finished with about 30 seconds to go. So thank you very much for your time today. And any other questions, feel free to grab me afterwards and we'll be good to go. Thank you.